I'm wanting to talk about a project that we started a couple months ago, which we call adaptive computing and multi-fidelity learning. This is in collaboration with a bunch of people at NREL, including Mark Day, who also used to be at Berkeley Lab, just like me, and also moved to NREL. It's a great place to be. Hillary Egan has done a bunch of work here. Ryan King is involved, Kevin Griffin, and Jibu Sandhya. A word of warning, there won't be many results in there, not many examples. This is more of a talk of like, there's some ideas that we have, things that we're currently working on. So I'm happy to have more or less of a discussion here in terms of, this sounds cool, but I don't think you can actually do it. I'm open to this. So let's get started. So what we're thinking about is that if we wanted to, maybe another word of warning, there's not that much of workflows in here, like most other talks had. So what we're thinking about is complex systems and scaling them up. And the fact that whenever you do a scale up of something, you have risks associated with that. Now, where do those risks come from? Let's say you want to extend a system or a process from laboratory bench to function in the real world. There is some sort of an uncertainty associated with it. And one of the uncertainties comes from you starting now to extrapolate beyond your known regimes. Oftentimes what happens, I can hardly see anything over there. Oftentimes what happens is that when you increase your scales, your spatial and temporal ranges of your experiments or simulations, suddenly you have new physics pop up or enriched physics that were not present on your small scale, maybe bench scale reactor, for example. You have high fidelity physics-based models. Maybe they're based on computational fluid dynamics that can capture those new physics on those larger scales, but they're really, really, really expensive often to evaluate. And then become a little bit impractical when you try to do optimization and certainly quantification type work. And then lastly, the operational regimes of existing experiments are quite limited. And if you want to do new experiments, maybe you have to buy new equipment, for example. Now you're kind of like trying to make an investment in new equipment, but do you know what kind of equipment you need in particular to get to where you want to go when there's all this uncertainty around? So adaptive computing, the way that Mark Day defines it, is the orchestration of a multi-fidelity model hierarchy and/or an experimental campaign to arrive at the best goal-based solution with well-characterized uncertainty given finite resources that we have. And so here's a little flow chart. So let's say, oopsie, sorry, my bad. There we go. So let's say we wanted to do some sort of an optimization task, some sort of uncertainty management down here. So we have a quantity of interest that we want to do uncertainty quantification. Now we can have multiple levels of model fidelity and real-time experiments. So the question is, how do you connect your simulations and your experiments with each other to sort of like get an insight of what's going on in your system? But you also sort of like restricted by, in a computational sense, by the computational resources that you have available. So how can you basically solve an optimization problem with uncertainty management using multiple fidelity models, but then also taking into account that you can't just like run a gazillion of huge simulations here. And I'll go through these two steps a little bit here, talking first about multi-fidelity models and how we can use them in optimization regimes. So multi-fidelity modeling. So whatever application you can think of, there are quite often, there's a large range of different fidelity models available. You have experiments, those are basically your ground truth, maybe the most expensive thing to obtain, maybe not computationally, but time-wise. You can have high-fidelity simulations of that same experiment that you have, and those simulations are based on partial differential equations, ordinary differential equations, but they take forever and a day to run. But then you can go from your high-fidelity model to, oh, maybe I throw away some of the physics, or I'll make my mesh a little coarser, or my time steps larger. Now, these expensive models become a little bit cheaper, but you lose a bunch of fidelity along the way. And then lastly, you can think about data-driven models. Maybe you don't have any physics in there, they just learn from input-output data sets. Maybe they have a little bit physics in there, like the physics-informed neural networks, but they're generally basically the cheapest type of model that you have. So now if I was to do some sort of optimization task and certainty quantification task, I have all these different fidelity levels that I can use. So how do I use them to get to my solution? Now, before I go into talking how we use multiple fidelities, I'll first talk a little bit about black box optimization. And Marcus is not here anymore, but it's very similar to what he basically talked about. Let's say I have a simulation. I want to do an optimization task with that simulation. I write down my optimization problem. So this is where your optimization needs to be good already. You need to model this problem somehow. So you have an objective function f of x you want to minimize. Maybe you have some constraints flying about. And your parameters x, they live in a parameter domain, closed. The problem we often face, and like I said, we're only thinking about high fidelity models right now, is my function evaluations for the objective function and or the constraints are the outputs of black boxes. So I can put a parameter vector in this black box, I wait, I get function values out. I don't know what happens here in between. Another issue with these problems, these high fidelity models often is they take forever and a day to evaluate. So we're talking hours to days. So if you were to do optimization, you don't want to do thousands of these black box evaluations. Gradients, quite often not available. Approximating them, not a good idea, because if you were to do finite differences, you need a bunch of function evaluations. Each function evaluation is expensive. So you're a little hosed there. And then the objective function often is multimodal. It's a black box, we don't know what it looks like, but in practice what you find is there's often multiple local and global minima. A local minimum is basically the best point in a small vicinity that you're looking at of the parameter space, whereas we're always after the global minimum, the overall best solution that you cannot improve however you adjust your parameters. So how are these problems solved? We're going back to the surrogate models here. Again, Marcus talked a little bit about that. So what you would do is you would approximate your objective function, f of x, with a surrogate model. The surrogate model is computationally cheap to build. It just learns off of input-output pairs. You can build a surrogate model for your objective function. If you have compute-intensive constraints around, why don't you just build a surrogate model for your constraints as well? And there's a boatload of different surrogate models you can use, from radial basis functions to Gaussian process models with a load of different kernels. There's splines you can use. Engineers quite often like to use polynomial approximations and so on and so forth. And then in optimization, yep.
Can you help me understand the surrogate of the constraint function? Like, the surrogate of the objective function makes total sense to me, but the constraint I'm struggling with.
So the constraint is really just, it's also just a function, right? So you would, where is this? So this is your constraint, gi of x is really just a function, like x1 plus x2.
Must be less than or equal to 0, or?
Yeah, at this point I don't care about this. When I want to approximate it, I only approximate the gi of x.
Just so that you can evaluate whether or not you are less than or equal to 0.
Yeah, or you
rapidly.
Like approximate.
Right, okay, thanks.
So it's really just a function, and I build a surrogate model for it, and then I check where's the surrogate model predicting that my value is less or equal than 0.
Gotcha.
That's how you can build a surrogate of the constraint. Which comes in handy when your constraints are really expensive and you're trying to probe somewhere. Do you want to evaluate the objective function there? You have to like first run it through an expensive constraint, takes forever, and then you see, oh, it's not feasible. Well, so you can use the surrogate model to at least give you some idea of whether or not a point x would be feasible.
Gotcha. I think I'm used to cheap constraint functions, is why I was confused.
All right, so loads of different surrogate models we can use. We heard about Gaussian process models before. And then the idea is to really, in the optimization that you do, you're trying to rely on the surrogate model to tell you where in the space omega you want to evaluate your objective and constraint functions. So here's a little flow chart of how pretty much every surrogate model algorithm works. You start out with an initial experimental design, so you go in your space, maybe a hypercube design, collect some points. You do your expensive function evaluations here, so that's where you query your black box. Maybe if you're trying to optimize an experiment, this is where you do your experiments in the laboratory. And now you have these input-output points. Have you reached a stopping criterion? If not, you fit a surrogate model to it. And then you ask the surrogate model, please tell me where to select the next function evaluation point. It gives you one or several points. Do expensive function evaluations, and then you just keep iterating. And usually, the way we stop here is not because we're at an optimum, but because we run out of computational budget in the end. And you think, this looks very easy. I can do this for any of my black box problems. But then as you start solving actual problem, you see that this step in particular needs to be adapted for problems that have constraints, that have integers in the variables. Sometimes your simulation doesn't evaluate, and it just gives you like, yeah, no thanks, no value here, which is a problem when you try to update your surrogate model. You have noise sometimes in the function values or in your experiments, or maybe you have multiple conflicting objectives you want to evaluate at the same time or optimize at the same time.
I guess this is where the adaptive computing comes in?
Sort of. Can I push your question to a little later? All right, so surrogate model algorithms. Here's a little illustration on a 2D example. You start out with your initial experimental assign. Maybe I collect 4 points in this 2D space. I have 4 input-output data pairs. Great. I fit a surrogate model, which again, it's accurate at these points where I know the function values, and everywhere else it's just a best guess of what the function looks like, right? And then you ask the surrogate model, please give me an idea where I should be sampling next. And it says, over here looks very promising. So you evaluate your function. Now you have 5 data pairs, so it would be a shame if you wouldn't use this extra piece of information, so you update your surrogate model. And then you just keep doing the same thing over and over again. You use the surrogate model to tell me, where do I evaluate next? I get a function value, I update the surrogate model, and so on and so forth. And then hopefully, eventually, I get somewhere close to the optimal solution.
Just a quick question, because sometimes people refer to this as acquisition function.
Yes.
Okay.
That's the same thing. The acquisition function is basically what tells you where to select this point.
But it's like, if you don't have uncertainty, it's your surrogate model prediction. If you have uncertainty, you combine the predictive mean and uncertainty into the acquisition function, right?
Yeah, I'll get to that in a second, where I'll talk about 2 different ways of how we can use the surrogate model to make this point selection. All right. Great. So all of this was just shown for a single fidelity level when everything is super expensive. Now, there's some literature out there that says, like, here, you have multiple fidelity levels. How can you use them? And basically what folks do is they assume that they have a low fidelity model that is computationally very, very cheap to run, maybe takes a fraction of a second. And I want to approximate the high fidelity response, somehow using this low fidelity model. And there's ways you can do it by just multiplying the low fidelity model with some function, by just adding something to the low fidelity model to get to an approximation of the high fidelity. Or you do a hybrid between the two, where you do like some multiplication and addition. Maybe you're all fancy and you put some weights in there too. So there's ways, different ways. There is no true answer. This is all usually whatever works best. So here's a little example of that. So assume that this is my low fidelity model. Evaluates really quickly. Assume I know what this difference is between high and low fidelity model. I can just build a surrogate model of this difference. And now if I add low fidelity in this difference, I get out this kind of a surrogate model here. Now this difference model is basically just built off of a few sample points that I collected. But you can see that the corrected low fidelity model looks very different than the actual low fidelity model. And just for comparison, this is what the ground truth, the true function, looks like. So it's not optimal, it's not the same, but it's way better than this low fidelity model and just relying on that thing. Now, if you were to run with this and say, okay, this is good enough, I don't want to do any expensive function evaluations anymore, you can see these yellow dots are where the true optima are. If you were to only optimize over the surrogate model over here, you don't really get to the true solution, but you probably get close enough to a very good solution. So then how can you use multiple fidelity levels in active learning? And acquisition functions, iterative sampling. So on the one hand, we have to think about low fidelity models can be either very, very cheap or they can be multiple minutes. It really depends on what the computational expense of the low fidelity models is so that you decide how you actually use it. So here we have, maybe we have a low fidelity model that's computationally non-trivial. It takes a couple minutes to evaluate. The high fidelity model maybe takes a couple hours or days, I don't know. But I can, if the low fidelity model is computationally non-trivial, I cannot do thousands of function evaluations there either, so I have to be a little bit smarter. So what you can do again, you can just build a surrogate model of the lower fidelity model, but it's usually based on more function evaluations because maybe for one high fidelity function evaluation, you can do 10 low fidelity evaluations. So you have a bunch more data based off which you can build your surrogate model for the low fidelity model. And then you would basically ask the low fidelity model, well, give me some suggestions of where I should query potentially the high fidelity model. The problem is that this low fidelity model doesn't necessarily have to be very much representative of the high fidelity model. So there could be some areas that are not very well correlated. So if you were to only rely on the low fidelity model, it can also just send you into the woods and you will never find your optimal solution there. On the high fidelity side, we usually do fewer function evaluations because they cost a lot. So the surrogate model is also a little bit less accurate because it's built off of less information. But if you build the surrogate model of the high fidelity function, you can basically use it as sort of like a second check of whatever your low fidelity model predicted you where you should sample. You can check it with the high fidelity surrogate and see if you're actually somewhere in a good regime. That'll also help you to understand how good your low fidelity model is. Now, back to Gaussian process models. So there's two ways. So we can either build a surrogate model of the low fidelity model and a surrogate model of the high fidelity function. Or we can think about using Gaussian process models. They're quite neat because they can combine the information from multiple fidelity levels into a single model, which is great. There's this toolbox over here, and if you're ever faced with multi-fidelity problems, this is a really cool toolbox to use. So now this is our image from before, is our low fidelity model approximation with the sample points. It's the high fidelity model with the high fidelity sample points. And a Gaussian process model can just merge these two kinds of information into a single surface. And again, here's a comparison to the true surface. And you can see neither the low nor the high fidelity approximation looks anything like the truth. But if you combine both pieces of information in a Gaussian process model, you're already like pretty close. Again, not optimal, but you're close enough. And then coming back to the sampling procedures. So in Gaussian process models, so this is the step down here. In the Gaussian process models, people like to use expected improvement. You balance local and global surge given the prediction, yes?
On the previous slide, I'm a little confused how the combination of low and high fidelity model gets closer to the true surface because you don't have any data about the true surface in the Gaussian process model.
The data about the true surface is really just these red dots.
That's right, but that gives you the also what you're plotting there is the surrogate model for the high fidelity model, not the actual high fidelity model. So the true surface is a high fidelity model.
No, the true surface, oh, this is my ground truth. This is a toy example. I know what the true surface is.
But the ground truths, if you have no data for the ground truths, how would you approximate it?
I do have data for the ground truth. And those are those red little dots here.
The red dots are actually from the ground.
Yes.
Now I'm fine. So this is the surrogate, the Gaussian process for the high fidelity. On the red points, it gets the right model. That's what you're saying.
Correct.
Yeah.
And it integrates both the true data from the high fidelity and the red dots.
Those are the right ones. Yeah.
Yeah. And it also uses the black ones, which is the low fidelity model. Basically bakes in a correlation function and boom.
Puts the intermediate, the stuff in between and shifts it around appropriately. I get it.
Mm-hmm.
I have a question. So for example, for the left bottom of the picture, so those kind of red points are given. So you try to find some service to pass through those kind of points, am I right?
To what do with the points?
So the red points are given, am I right?
Yes. Yes.
And you wanted to find some surface passing through this kind of surface.
Correct.
This kind of points.
Yeah.
Right? But we have infinite many of these kind of surface.
That is true.
Then what is the criteria for you to choose uniquely?
Well, the way Gaussian process models work is, this is just my average prediction of these infinite many models I can fit to these points. If you think about a Gaussian process model in a one dimension, you would basically fit many different models to the same data.
So you use
And then the
Gaussian
average,
function as the base to fit this kind of stuff, and probably choose some different coefficients, right?
well, yeah, there are, you optimize the hyperparameters like the length scales of the Gaussian kernel in there, and some other parameters.
Okay, that is one application you minimize so that those kind of very close to what you want to interpolate.
Yeah, but you're right. I mean, the Gaussian process model is basically probabilistic. And what is shown here is really just the average of many of these different models. What I'm not showing is the standard deviation between these models.
I see.
Yeah, because what you learn essentially is a multivariate normal distribution, right? And so you're showing the mean.
The mean, yeah, exactly. Johannes, did you have a question?
I got it offline.
Oh, okay. In parallel. Okay, sweet. So the way we sample, different methods have been developed for being used with different types of surrogate models. The Gaussian process folks, they like to use expected improvement. So here again, we're looking at the prediction of the Gaussian process model, the mean value of the prediction, and we take into account the standard deviation of that prediction as well. And now we basically, in expected improvement, we trade off basically the uncertainty, the standard deviation, and the predicted how much better are we going to get. People like to use this. They say it balances local and global search. You can also do a mostly local search where you just sample at points X that are maximizing the probability of improvement. You can use lower confidence bounds, minimization case here, of course, that can be more local or more global depending on how you choose kappa. I don't know. Again, how are you gonna adjust kappa? I'm not sure. I never used this actually, but it's there. And here's a little cartoon that Kevin gave to me. Up here you can see in the black curve is your true function that you want to approximate. The blue curve is your Gaussian process model mean prediction, and the blue area is basically uncertainty estimate that comes with the Gaussian process model prediction. And now what you see here are these three different sampling strategies, and this example is for maximization. So expected improvement you can see here is like a little wiggly function, upper confidence bound, so now you would maximize the upper confidence bound. Also very many local optima here. Probability of improvement you can see goes all over the place. So now you might already say, okay, if I were to sample in this step based on expected improvement, then how the heck do I know I'm here at the global maximum of the expected improvement? How do I know I'm at the maximum of the upper confidence bound? Well, the reality is you actually don't. And what actually happens in practice, or what happens to me a lot if you take Gaussian process models off the shelf and you use the expected improvement, is the following. So here's my Gaussian process model approximation, my mean approximation of the data. And here's the expected improvement function. And now I'm trying to sample where this function is maximized. So ideally, I'll find this point over there. But I use generally just a local search to do that. So if I start here with my local search, I go absolutely nowhere. If I start over here, I go nowhere. It's all flat over there. And you start seeing that more and more, that the more sample points you throw in your space, your expected improvement becomes flat, and then it just has these very tiny little peaks at which you're trying to sample, but quite often you don't find these peaks. And then you do random starts for your multi-start optimization, and then your algorithm seems to be sampling more or less randomly because it constantly keeps getting stuck. So there's some improvements that are needed here. All right. So, and then another approach you can do, you just say, I don't want to do any expected improvement or stuff like that that's more advanced. Maybe you have a surrogate model that doesn't have an uncertainty estimate. What we like to do then is we go in our space, read our evaluated points. I go to the best point I've found so far, this yellow star over here, and then I just add a bunch of random perturbations to it and create a large set of candidate points. And then out of these candidate points, I select one or several for the next function evaluation. And ideally, I want candidate points that have a low predicted function value, because it means they are probably going to improve the best solution I have, or that are far away from already evaluated points, because usually when you go away from where you have information, uncertainty is larger, so you kind of like add to your global information of the model. Okay, are there any questions so far? Surrogate modeling, sampling, active learning? No, great. Everything is clear. There will be a quiz in the end.
How does that change with dimensionality is a problem you just mentioned, that finding the optimal point to look next is actually something where maybe you need another surrogate model in order to find those. Does it get worse with dimensions? Probably, right?
Expected improvement from experience gets way worse. This like more or less stochastic search over here, adding random perturbations.
That doesn't care too much.
That doesn't care too much. It's really just like evaluate, basically solve a linear system of equations.
You're staying pretty local is a problem, right? And
You're
high
staying-
dimensions, there's a pretty good chance your optimal is somewhere else, right? Than that one point you have so far.
Yeah, and it goes a little bit too philosophical, but in high dimensions also, when you go to your best point found so far and you perturb all parameters of all dimensions, then you're suddenly like all the way over here.
You're actually pretty far, right? so maybe that's okay.
So doing a local search becomes more difficult.
So it's pretty random is what you're saying again, right?
Yeah. This is the best we can do for you, so. All right, so multi-fidelity model. So now I only talked about mostly sampling strategies, but now I need to sort of like, let's say I know where I want to set, like I know where in the space I want to sample, but how do I know I'm going to like use a low-fidelity model or a high-fidelity model or something in between? And again, it's important to think about exploiting all the information that you have, but also being careful that this low-fidelity model, this guy over here, may have nothing to do with the truth, the high-fidelity ground truth over here. So if I were to sample n points and I run the low-fidelity model, which maybe takes 10 minutes per evaluation, it'll like give me information that's not really helpful for finding the optimum of the high-fidelity model. So some things you can think about is if you had access to a surrogate model of the difference between the low-fidelity and high-fidelity model, and I select my n sample points, I can look around in the space and basically look if the points I want to sample are in regions where the difference between a high and a low-fidelity model is quite small. That basically indicates that both functions are somewhat similar, at least in that area. And in that sense, I can say, okay, maybe I selected a point that's down here, is somewhat similar between low and high fidelity models, so I evaluate the low fidelity model to see if that gives me any improvement of the data I have so far. And then I go from there to sampling the high fidelity model. A little bit of a hand-wavy argument here. Okay, any questions so far? Otherwise, we will go to the more or less adaptive computing part of this. Yes?
I mean, the low fidelity model may not be helpful, but can it make the results worse?
Oh yeah. If you rely blindly on this guy, then it just can send you somewhere into an area where, like it says, it's low over here, sample over there. But then you look at the high fidelity model and it's got no good values over there. So blindly relying on this guy is not a good idea. This is where you always need to double check a little bit.
So can you have more than just two models, like multiple fidelity
Yeah.
levels? Okay.
Yeah, you
Is it
can.
common to use?
What's it?
Is it common to use? I've seen a lot of examples of like low and high fidelity. I don't see much examples of it.
Yeah, I want to
We
say.
have like with simulations, we have different levels of approximations, right? So
Yeah.
multiple fidelity levels.
You can. I know a bunch of folks at CU Boulder. They're working in wind farm simulations, and they have multiple levels of fidelity.
So, is the low fidelity model, the reason why you're doing this is because it's low compute? That's why.
Yeah, it's cheaper.
Yeah. So if you can get away with it, you'll use that.
Yeah.
Got it.
And hopefully it doesn't like send us in the wrong direction. But quite often we don't know that because it's a black box too. Or like, I don't know what the surface looks like in reality.
Can I ask one more quick question? So here we're talking about simulations, expensive simulations and cheap simulations, but I guess we could also use actual noisy measurement as high fidelity, while low fidelity will be some theoretical simulation, right?
Yeah.
So that's also...
Yeah, that's correct. Good point. I was supposed to say that. So you can have simulations and here low fidelity, high fidelity. You can have an experimental setup with like different types of characterization methods. Some of them take forever and a day but are highly accurate, and some of them are kind of like medium fidelity.
Can we make any statements about the properties of the difference? So are there, for example, different frequencies? Like or to identify this, that we have different frequencies for the low fidelity model compared to the high fidelity. For example, that maybe the high fidelity model is more smooth, more physically reasonable. In our low fidelity model, we have maybe oscillations which come just from not converged calculations.
I don't know that. I feel like if you, as the domain scientist, know that that is a fact, that the low fidelity model tends to oscillate more, then maybe there's something that you can bake into the surrogate model to represent that and exploit that extra information. Right now, this is really just based on input-output, assuming I know nothing in between. Johannes.
Do you need to know if one model has a higher fidelity than another? So you can maybe imagine a situation where you use different approximation schemes and you have no a priori information about which one's better.
Aha. I would very much like to know on a scale from 1 to 10 how accurate the output is, but I can't.
You made a learnable parameter then?
Yeah, exactly. Like if this could be like a learnable parameter.
Yeah.
Because we can solve all problems by throwing more machine learning at it.
That is true. Okay. I'm not sure how far I'm gonna get with this talk here. I'm gonna head on here into the goal-oriented solutions, and this is something is gonna be a little bit more or less not so well formulated now. But let's say we have low fidelity models, we have high fidelity models. I want to sample a bunch of points. The question is, where am I going to sample them? Maybe I have access to some sort of edge computing, have cloud computing, have an HPC around. Maybe I can do some experiments. If I now want to decide, do I do low fidelity evaluations or high fidelity evaluations? Where am I going to run these simulations or evaluations, right? And what basically, in the end, what it boils down to is a stochastic optimization problem, I think. Debbie might correct me there. So the current modeling paradigm, what you see quite often is we either have models that are based on first principles or purely data-driven models, or you're somewhere in between, but you just like chug it onto one machine and then you run it there. But what happens if we can actually bring in a second dimension where we can decide where we want to run each of our different models? So maybe we have HPC over here all the way to like edge computing. Now, if I say I want to do a very computationally expensive high fidelity simulation, that's probably going to be based on first principles, I have to put it on HPC probably. I can do one function evaluation, but for the price of one of these expensive function evaluations, I can also do many, many like lower fidelity function evaluations, and I can just send them to a different compute device. So the idea here is to figure out, as I'm sampling and thinking about my low and high fidelity models, like where am I going to run them to be basically most efficient and exploit the compute resources that I have available. So I tried to write this down as an optimization problem, and I'm not 100% sure if I'm happy with it. So there might be some corrections needed. I'm also like interchanging here a little bit fidelity level and resource availability. So let's say I have endpoints selected where I want to do function evaluations. Now, in order to figure out on what resource to run my function evaluations with low or high fidelity or medium fidelity models, maybe I can solve this optimization problem, where perhaps my objective function is some sort of a benefit that I get of evaluating a point xi at a fidelity level J on a certain resource that supports this fidelity level. Now, this benefit could be like an accuracy measure or something like that. But now I have to take into account that at each step, every time I evaluate, there's a total resource restriction. So ideally, I know this before, and I know how many resources it requires to run a point at a certain fidelity level on a certain piece of architecture. And then each type of resource also has its own restriction of how much I can run there. So in theory, if you were to maximize that and you didn't have any of these constraints, I would just run every point at low fidelity, every point at high fidelity, and I would maximize this function, but I cannot wait that long, basically. So I think, oh yeah, and the thing I forgot, this is maybe going back to what Johannes talked about earlier. The resource consumption is a little bit stochastic here. Even though you think your function evaluation might take 5 minutes, like putting it on and getting it back, it'll take 5 minutes, or maybe it takes 15, you know. So there's a stochasticity here. I don't know how it's distributed yet. I have to think about this more. And this is basically our framework on how this whole multi-fidelity thing works. We have an adaptive computing driver that sort of like is able to communicate with some sort of a resource manager that can check like every time I want to do function evaluations, what kind of a compute do I have available? So you solved this cool optimization problem from earlier. The driver is also informed by application-specific code, being like I would have to tell it, do you want to do uncertainty quantification, optimization, and so on and so forth. I also have to give it the fidelity levels in some shape. And I need to also tell it what sort of statistics I want to have out of it. And then this adaptive computing driver would basically interact with these boxes all the time to find maybe an optimal solution or solving an inverse problem. But again, this is still work under construction, so don't take this as the final thing. And now I have, I don't know, like 5 minutes or something left. 2 minutes? 10 minutes. Excellent. Thank you very much. So I just want to talk about, so this is sort of like the framework we're trying to do. There's resources we want to optimize, different fidelity levels we want to use in optimization. And I'm going to talk about 2 examples that we want to apply this to. But before I get there, are there any further questions about this very convoluted thing? Yes?
Can you just explain on the last slide what the zeta ij sub ij was?
Yeah, that's my randomness here, my stochasticity. So did I write this here? Oh yeah, here. So Tj of xi is the resource consumption if I evaluate a point xi for fidelity level j. So it's basically, imagine it's a time. Okay. So I want to evaluate xi on the edge, and I know approximately the time it takes to do that. But the notion here is that I know it approximately, so there's some stochasticity in here. So it's not going to take exactly 2 minutes, but it takes 2 minutes plus minus something. So that when you have this constraint, and again, this is a little bit of sloppy formulation here, you have the stochasticity in here, and now the question is, do I want to satisfy a worst case of the constraint? Do I want to satisfy this constraint and expectation? I do not know yet. Other questions? No? Good. Okay. And now I talk about 2 applications, and I will not claim that I am an expert in either of them. I don't know why it keeps jumping ahead here. So we have at NREL ARIES, the Advanced Research on Integrated Energy Systems. So basically, when you have energy systems, you generate energy somewhere, you have a demand. So maybe you live over here, maybe your neighbor is over here. You all need energy. We have a lot of renewable energies that we're trying to get into the grid. But renewable energies are like the wind isn't blowing all the time, the sun isn't shining all the time, so sometimes we have more, sometimes we have less. But kind of like you have your demand, you don't want to just like suddenly have the lights turn off because the wind isn't blowing or something like that, right? So then the question is there some sort of a flexibility in the grid that we can exploit so that we can meet the demand with what we generate at different times of the day? And ideally, we want to bake this into an adaptive computing framework, like I just explained. So how much demand flexibility is there available, can we exploit to support the grid. So, and what we're trying to do here is to understand, evaluate, and predict the demand flexibility that a device or a building or any community can provide. So this can be done, for example, by shaping energy demand to support certain grid conditions, but to also like be able, in extreme conditions, to provide this extra grid flexibility there. Challenges here are that it's very, very difficult to compute the anticipated energy demand and to understand what are the opportunities to exploit optimal control for energy demand. So this is computationally very expensive, but things you can control, for example, like your HVAC system, turning off your lights, for example, doing like preheating or later heating, for example. Another challenge we have in this problem is that we have some real world data, we have some approximations of what's going on in the real world. That data doesn't represent everybody. There's areas where the data is very unreliable. So there's some uncertainty in here as well. So folks have built surrogate models of the data of communities, cities, and so on and so forth. But there's a whole lot of things you have to think about when you're trying to optimize basically the demand or trying to maximize the flexibility of the grid. Generally, what we have thousands of parameters that are in these models. Hundreds of them are important. I don't think anyone has done a sensitivity analysis really on that. You don't necessarily represent all possible building types that you have. Maybe you have newer buildings, you have a bunch of older buildings, people with different devices installed, different charging schedules for their EVs. We have a bunch of weather conditions that actually play into your energy demand. If we had to make scenarios for all of these weather conditions, it'll take forever and a day, so people generally don't use it. And if you, let's say, you understand for a certain region what the demand and supply of energy is, it doesn't just like translate to any other region. So maybe you're in San Francisco and you understand what's going on. You can't just move this out into Denver, which is a way different climate, for example. So now we're trying to bake this whole somewhat widely explained problem into our adaptive computing framework. So the first thing we're trying to do is like identify what our objectives are. So maybe like our objective is to optimize control of the grid or to optimize the schedule of heating and cooling and how we can do it, and there will be models for that. The models that we have, so this is basically your fidelity levels over here, you can think about there's something called the Energy Plus model, which seems to be a very high fidelity model, but it takes 1 to 30 minutes to simulate one building for a year with 1 minute time steps. If you think about any neighborhood, this is a single building. There's a lot of buildings out there. There are other models like Ochre that are made for residential areas only, so maybe they're a little bit less fidelity there. Then there are reduced order models that also run quickly, but they also, again, have limitations. For example, you can only simulate them at 15-minute or 1 hour time steps. And all of these models are pretty much deterministic, highly nonlinear. So once you build these models for a certain area and you go out of that area, they become very unreliable and have higher uncertainty. Is that the right? Yep. Cool. Challenges are that scaling these simulations to larger communities is extremely difficult. There's a lot of uncertainty attached to it. Suddenly there comes some discrete optimization in there. So it's a very difficult problem. I don't have any results here. We're still trying to form the problem and define the problem well. But we do have some data on this place in Colorado, Peña Station, where there's about 150 buildings around. 50 of them have been defined already. There are multi-family buildings, and guess what? There is some extra challenges if you have a multi-family building that you're trying to control. We have Energy Plus models and reduced order models already built. And then, we're on the way of trying to at least get the models set up and trying to optimize them then. So that was a little bit a hand-wavy. This problem just started. And then I want to have one last example of the last few minutes that I have. Example applications is in virtual engineering of biofuels. So some part of NREL is thinking about how can I make biomass into biofuels. And again, I don't claim to be an expert here, but I'm told that there's a 3-step chemical process over here. Some of these words I can probably not even say. So there's a pre-treatment step over here, and then enzymatic hydrolysis, something like that. So, so there's these three, and then there's the bioreaction itself, and these 2 yellow boxes here. You can either do with a high-fidelity model, or you can approximate it with a surrogate model. So there's this multi-fidelity aspect coming in here. And our objective, again, in our adaptive framework, computing framework, maybe we want to maximize the reactor averaged oxygen uptake. We have an order of 10 chemical and processing design parameters that we can tweak a little bit, and then we can define our different fidelity level simulations. Maybe the highest fidelity level, everything is a high fidelity model, and maybe it takes 57 hours to basically go from input to output. Maybe there's a second fidelity level where I say, the first step, the pre-treatment, I use a high-fidelity model because that's pretty cheap, so why don't I use that one? But then I use a lower fidelity model for the second step and a high-fidelity model for the bioreactor. You can add more fidelity levels in here, like the first one being a high-fidelity model and the 2 last ones a low-fidelity model. Maybe one of them is a data-driven model or parametrization, what have you. So here's a couple of parameters that were optimized. And then I don't know if this is going to show up. This is going to be hard to see. But Kevin did a little bit of a preliminary optimization where he just took a Gaussian process model, Bayesian optimization off the shelf. He tried to tune 8 parameters on the low fidelity model. So each run of the low fidelity model was really just a 5-minute thing. Now, what you see over here is this sampling history in a sense, where on the x-axis, you show the distance between between the solution that you found and the true solution. So if you find the true optimal solution that I know, you should end up at 0 over here. And the other thing is what's shown in the color is basically representing the iteration of the optimization algorithm at which a solution was found. So if you had a gradient-based algorithm, you go down the hill and every sample you take, you get closer to the solution. So in theory, if you had gradient-based algorithm, everything down here would be red because you find these points later, and these guys would be blue, but it's not gradient-based, it's a sampling method. So you can see that the last solution was somewhere over here, pretty far away from the true solution, and that the actual true solution, the best solution, was found pretty early on by the Gaussian process model. This is just an illustration of how to think about analyzing your results and the algorithms. And then the other cool thing that, of course, happened is that your low fidelity model may actually not evaluate for some parameter settings. And so this was like the first, we're going to just try this out and see if Bayesian optimization works on this low fidelity model. And then you realize that for some regimes, where the model is actually defined, it doesn't give you a function value back. So it's what we call hidden constraints. We know how to deal with this, but this makes our optimization way more difficult. So there has not been any multi-fidelity business in here yet, but we're going to get there step by step. So to conclude, hopefully we will be able to develop this adaptive computing paradigm, which will then allow us to make efficient use of the computational resources that we have and reduce the associated compute costs. Hopefully it'll allow us doing uncertainty quantification using multiple levels of fidelity to get a proper handle of like scaling up systems and processes. And then hopefully we also get eventually to scaling up laboratory experiments with a well-quantified uncertainty. So, done. Thank you.